Welcome. Let's come back to our videos and let's talk about our discussion boards from last week. Let's go to this first problem, which a lot of you actually had a lot of struggles with. I saw many of you simply going with the 7 factorial or 4 factorial and 3 factorial. That would be true if we were talking about a 7-letter word, but we're talking about 5-letter words, which the way to manipulate this is not by multiplying or dividing. It's literally we'd have to subtract out how many 6-letter words and how many 7-letter. So I start with 7-letter words minus the 7-letter words and the 6-letter words. So that doesn't make sense because these are discrete sets. That's part of the problem we have is that 6-letter words don't live inside 7-letter words. So it's really hard to find the exact number of 5 letters. I mean, you could say I'm going to pick 2 letters to drop, but if you start trying to pick 2 letters to drop, what if they're the same? What if they're different? Lots of problems that we have going on here. So the better way to attack this problem is to say, let's just start looking at cases to understand this. The number of B's that I'm going to use is either 1 B. I can't have 0 B's because otherwise I would have I don't have enough A's. I only have 4 A's, so I have to have at least 1 B to get to 5 letters. So I have 1 B, 2 B's, or 3 B's. Let's break this down, look at each of those cases. Let's start with the first case. If I have 1 B, then we're picking the place for that B to go. Because remember, that B is going to have to live in one of these 5 spots. Now, what if I number these spots 1 through 5? And so you're really picking the number 1 through 5 that the one that goes in. Well, there's 5 possible numbers I'm choosing 1, so there's 5 of them. What happens if I'm choosing 2 of them? Well, I'd pick the 1 and I pick the 3. That's no different than, because remember, order doesn't matter. I'm picking the number that corresponds to the spot because the order doesn't really matter. 1 and 3 is the same thing as 3 and 1. And for that reason, it actually turns out that we would get for the next 2 cases 5 choose 2 and 5 choose 3. So if we add all those together, we get 25, or you can use the summation notation to also just show. I know this is really simple because it's adding up 3 things, but this idea that I'm going to add up the distinct cases because they actually are totally disjoint. So, I can have exactly 1, exactly 2, or exactly 3. And this is the key thing to kind of understand and utilize. Let's talk about this permutation problem because a lot of you had problems with this one as well. I want to warn, kind of the idea is, yes, you can go use the derangement numbers, but make sure you understand what the derangement numbers are. What's their formula? Where does it come from? If you just build things just like using an algorithm, if you don't understand where it comes from, you really lose a lot of the manipulative ability of that formula because you only can use it in one specific situation where there may be other situations that are highly valuable. So let's consider the situation. Let's just make a table to understand our different n values and how many ways I can have 2 fixed. So if n is 2, we're going to start with 2 because obviously you can't have anything less than that. I'm only going to have one way that's fixed because if I have 1 and 2, they're obviously going to go straight to 1 and 2. There's no options. If I have 3, well, you fix 1 and 2, 3 only has one place to go, and that's 3. So this is only the case where if 2 of them go to, then all 3 have to go. So it turns out that number is also 1. What about 4? Well, to fully see this one, I'm actually just going to build it out brute force wise. And then I'm going to talk about, because I'm trying to look for the pattern here about what's going on. Because notice in these situations, I picked 2 of them and said how many were left. And that was the number that actually kind of helped me out. So in this situation, next one I have 1, 2, 3, 4. I'm going to use this different notation where instead of drawing arrows, I'm just going to write them on top of each other. So this means that 1 goes to 1, 2 goes to 2, and 3 goes to 4. 3 and 4 goes to 4. If I say 1 and 2 are fixed, then the only options I have for 3 and 4 are 3, 4, or 4, 3. Okay, we can do that because I have 2 ways in which to choose 1 and 2. Then I could pick 1 and 3 as being my magic pair. And they are now, if I make 2 go to 2, then 4 has to go to 4. So I obviously can't do that. I got to swap them. So there's only one way to do that, and that's literally to make them swap to a different thing. 1, 2, 3, 4. And then I have, if I can't do go 1 and 3 anymore, but I can go 1 and 4. So this one is all, this is all 4. It gets all by itself. 3 is also in the same situation. The previous step is exactly in the same situation. But if we skip down just 2 steps, I can now go 1 and 4, but these have to be opposites. Okay, so far we've gotten 3. And I've done actually the 3 possible cases where exactly 2 are fixed, and I'm setting, and the other 2 are not. Well, so let's move on, and let's move on to 2 and 3 being fixed, but that means the other ones are swapped. So notice a trend here. The last 2 are fixed because they cannot go to each other. So I have 1, 2, 3, 4. This 2 and 4 forces this to be a 3 and 1. And similarly, the last one is that 3 and 4 happen to be going to each other, and the 1 and 2 are switching. And so I have 6 for here. That means my next number is 7. That's interesting. So I had 4 numbers, I got 7. Now let's consider for a second 5 numbers. In this first situation, at least 5, I could have had all of these situations and just had the 5 go to the 5. So I have all these situations where the 5 goes to the 5. And that gives me 7 situations where 5 goes to the 5. But that's only when I have 4. If I had a 5 goes to 5, we have 7 situations we've already written down here. I'm just going to write down that 7 up here. Or the last. So I need to change all these in a way that we don't just have the 5 going to itself. So I'm going to erase all these boundaries, things below them. All right. So this first one, we're going to do this. We've already done the same. We've already done where 5 goes to itself. All the numbers go to themselves. We counted that. And we actually had all the cases. This was all 5, which, by the way, if 5 of them go to the same spot, it's the same thing. And then we have 3 because we had 2 of them fixed and then the 5. So the 2 situations, the only situation we have left to consider is what happens if I have 2 of them fixed. So let's start off the same way, we're 1 and 2. Now I have to mix these up. And how many ways can I mix up these so that none of these are the same? It's almost like I'm trying to do a derangement number on those 3 numbers. And this is the idea from which we can build and kind of leverage ourselves to have at least 2, but I'm going to add that in to the at least 3 and at least 4. But if I want exactly 2, I'm going to mix these up. So 3 can't go to 3. So if it goes to, it's got 2 options. It can go to 4 or it can go to 5. And if it goes to 4, then the 4 has to go to 5 and the 5 has to go to 3 because we don't want the 5 going to 5. Similarly here, the 3 went to a 5, so the 4 has to go to a 3, and the 5 has to go to a 4 to prevent them from going back to the same spot. Now, let's consider the next. We've done the situation where I pick the 1, the 2, and notice 3 could go to 4 or 3 could go to 5. Those were the only 2 options for it, and the other one was forced. That looks almost like a 2 factorial to me. Strange. All right, well, I'm gonna come back to that. So now let's say that 2 and 3 are the ones that are fixed. So these are the fixed pairs. So 1 has to go to another number. So we'll say it goes to 4. 4, 5, 4 has to go to a different number, and 5 can't go to itself. So 5 has to go to 1, and 4 has to go to 5 because we want exactly 2. Now again, if I fix the 2 and 3, the 1 can go to a 5, the 4 can go to 1, and the 5 can go to a 4. So notice for each of these situations, I'm getting a 2 factorial options because the first number has 2 options, then everything else is fixed. Well, that tells me that's n choose that's 5 choose 2. So I'm picking which 2 times 2 factorial. But that's also the same thing as 5 times 4, which happens to equal 20, because this would be 5 factorial over 3 factorial times 2 factorial times 2 factorial. Those things cancel out, and thus we get 20. So we have 27 because remember we took the previous number and we actually added one on. This is getting kind of interesting. So the question is, how does this pattern continue? Did you see an underlying pattern here of what we're counting? I was not trying to overload you and blast you through this because I'm trying to point out if we pick something, what is left over? Well, I have to mix up all those situations. And the question is, pick 2, what's left? And how can we write this down as a general formula? All right, I hope that helps. Let me know what other questions you have, and good luck.